lecturer is Professor Andrea Renzetti. Is it correct pronunciation?
Yes.
And he's from Okinawa. The University of Ryukyus, right?
Yes.
And today, Professor Hayashi is absent because of his daughter's wedding. So we hope the weather would not become bad. However, as you know, the typhoon is coming up. Okay? So I have asked Professor today's talk be short. So before, around after 4, we will be finished. So after that, you should go home as soon as possible, right? Okay? And then switch to Japanese, okay? 公共交通機関で来てる人。帰りのチェックはしてますか？ JR が動かなくなるとか、バスが動かなくなる可能性があるからね。だからもしそれ途中でもいいからブレイクの時にチェックしてダメだったらそこの段階でも安全なところ帰る。それは約束してください。僕ら君たちの事故で起こったら大変だからね。よろしいですか？ Okay, so shall we start?
Yes, thank you. Good afternoon, everybody. Very nice to meet you. I have already seen some of you yesterday, but most of you probably are new today, so very nice to meet you. Since I said, yes, I am from the University of Ryukyus. Originally, I come from Italy. And today, we will talk about drugs. Now, in Japanese, when we say drugs, we think of something bad, illegal drugs. But actually, drugs can also be good for our health. And today, we will talk about good drugs. First of all, so the title is Drug Discovery and Development. How are the drugs discovered? But before that, we should discuss what is a drug. You know, what is a drug? Any idea? Please don't be shy to discuss your thoughts. Any random thoughts? Anything is okay in mind?
薬について何も思うこと。
Yes.
Drugs are to become better our body.
Yes. Drugs are chemical compounds that make our body feel better. Actually, when do we take drugs?
I take them when I'm sick.
Yes. We usually take drugs when we are sick, and drugs can make us feel recovered, so they can help us fight against microorganisms that create disease in our body. So they are very, very important for our health. In the past, many drugs did not exist, and because of that, when people got sick, they had no drugs. They had very few drugs, so they could die very easily. And they only lived 30, 40 years, not longer. And nowadays, we have a lot of drugs to treat our diseases. And so our life expectancy is very high. Life expectancy means we can live, we can hope to live until much longer, 80, 90, sometimes 100 years. So they are very, very important. And then how are drugs discovered? It's important to know how we can discover new drugs. In chemistry, some scientists are trying to find new drugs very, very hard because they are so important. So how are the drugs discovered? Do you think it is easy to find a new drug, or is it difficult?
Maybe it is difficult.
Yes, it's actually very, very difficult to find a new drug. It takes a long time. And this is why this slide says it's very difficult. That it's like finding a needle in a haystack. If you want to find a needle, you have to search for a long time because a needle is very small. And finding a new drug is a little bit like this. So, let's say in the past, 100 years ago, 500 years ago, 1,000 years ago, there were very few drugs. There were no pharmacies, no hospitals to get drugs. So, what did people use to treat themselves? In the past, no hospitals, no drug stores to get drugs. So what did people use? Yes?
Maybe they used botanic things.
Botanic?
Botanic things.
Things, yes, botanic things. Botanic means something taken from plants. They used plants, herbs. Some plants do not make drugs, but some plants in nature produce drugs. And people in the past used to prepare potions. So you take a plant, you put it in water, you boil. When you boil, the water can extract the drugs from the plant. And then we get a potion. It looks so, in this case, this is a witch, our image of witches. Actually, when you prepare tea at home, you do something similar because you take tea leaves and you add hot water on it. In that case, after a while, the water becomes green or brown because the water extracts all the compounds in the tea. And then you get a potion. And the tea is also a sort of drug because it makes you feel better, it increases your attention. So in the past, this is what people used to do. And there is a plant that people especially used as a drug, which is willow. Have you seen any willow in Japan? Here? I don't know. Yes.
Yamami? He said in Japanese. Yeah.
Oh.
Willow.
You have?
Yeah, yes.
Oh.
We have.
Okay. So you have seen it. Yes. So it's willow is a very special plant because it has a lot of branches with leaves that go down like this, and it produces some sort of drugs. The drugs are located all over the plant, but especially in the branches and in the cork. The cork is the bark, is the part that surrounds the branches. It's the external part. So you can take the bark. If you put it in hot water and boil, water will extract the active components and you will get a solution, brown, that looks like tea, actually, and people used to drink this solution to relieve pain, headache, inflammation. Inflammation is a condition in which, for example, the skin becomes very red. When you have inflammation, when your skin has inflammation, it becomes red. And that means there is something wrong with that part of the skin. And you take this potion, the red part will go away, so you will get relief from inflammation. And this is a very important potion, and this is one of the very few that people had in the past. In Europe, this solution was used very much. There was a famous medical doctor. He was called Hippocrates. Many centuries ago, he recommended people to drink this potion to get a relief from headache, pain. But at that time, people did not know why it was active. Why is that potion active? People did not know. They drank it, but they did not know why it was active. And then that happened in the 4th century BC, means before the year 0. Now we're 2019, so 2019 years ago it was year 0. And then 400 years before year 0, people used to drink that potion. And then many centuries later, people found that instead of boiling the bark, you can also take the bark and grind it, make it into a powder, and then you can also use the powder itself, drink it directly. That's also active. And then chemistry developed, and the chemists became able to analyze this powder. What does this powder contain? And they found that this powder contains many compounds, but only one is responsible for the biological activity. And this compound is salicylate. And then the chemists became able to determine the structure of salicine, and they saw that the salicine has this structure. They also discovered that when we take this powder in the body, this compound is broken into 2 parts. So our body breaks this bond between oxygen and carbon. So the molecule is broken into 2 parts. One is active, and another one is inactive. It's not active. So people discovered something very important. Important discovery is that activity depends on the structure. If you change the structure of a chemical compound, the activity also changes. Okay? And so this part is active, but this other has a different structure, so it's not active. And then chemists thought, well, there are 2 parts. One is useful, but another one is not useful. So we don't need actually this part. This is not necessary. If we want to treat our conditions, we only need this part. And this part is called actually salicylic alcohol. When this bond is broken, oxygen then bound hydrogen. You get salicylic alcohol. This is the active part. And chemists then prepared salicylic alcohol in the chemical laboratory. So salicylic alcohol is is good for our body. However, it has two problems. First of all, it is weak. Weak means that if we want to treat our condition, our disease, we need a lot of salicylic alcohol. We need to take a lot. And that is not good, because if we take too much drug, it becomes toxic. The second problem is that salicylic alcohol is very bitter, bigal, the taste. So it's very unpleasant to have it. And then chemists thought maybe if we change a little bit the structure of salicylic alcohol, compound is still active, but maybe it is not so bitter, and so it would be better. So they modified the structure of salicylic alcohol. If you take out these two hydrogens and you replace them with an oxygen atom, you get a new compound that is called salicylic acid. Salicylic acid looks very similar to salicylic alcohol, but it has different properties. It is not bitter, so it's easy to take, and it is more powerful than salicylic alcohol. So we need a lower amount to treat our disease. However, it has another problem. It is irritating to stomach. Irritating means that the cells in our stomach actually start bleeding, and they get wounds, and they lose blood, so that's not good for us. So chemists had to modify the structure again. And then another modification is to remove hydrogen atom from this OH and replace it with another group of atoms, which is CH3 C double bond O. CH3 C double bond O is called acetyl. So when the acetyl is attached to salicylic acid, we get acetylsalicylic acid. And acetylsalicylic acid is actually as powerful as the salicylic acid, still not bitter, but is not irritating for the stomach, so we can use it. And this is the formula of the aspirin that we can find nowadays in the drugstores. So it took a very, very long time. So the important point is there are two sources of drugs. One is willow, and another one is the chemistry laboratory. The willow contains salicin, which is active. But in the lab, we can prepare a drug that does not exist in nature, but is more powerful. So the nature makes drug, but it is not so good, not so powerful. It is a little bit, it has some side effects. In the chemistry lab, we can do better than nature. This is what chemists try to do. They try to do better than nature, to create more powerful drugs, more active. And aspirin was only produced in the 20th century, so 100 years ago. It took a long time to arrive there. And then we have a couple of more slides, but since we have to finish a little bit earlier, I would like to skip some of them. Sorry, so this was supposed to be an exercise. Important. This is the structure of aspirin. Aspirin so contains three important parts. One is C double bond OH, which is a carboxylic acid. Another one is a ring, benzene, which is called benzene. And another one is ester, the remainder of the molecule. Now, when people find new drugs, they are always very, very excited because, yeah, we have a new drug. And when aspirin was discovered, people believed that aspirin could treat any sort of disease, any condition. And so some chemical companies advertised aspirin in a fantastic way. So this is, for example, an advertisement from Bayer, which is the company that made aspirin. And there's a dialogue between two women. One woman says, Jane, how can you possibly feel like shopping on a day like this? It's so terribly hot and humid. I have a headache and don't feel like doing a thing. So she said, Jane, I want to do shopping, but I have a headache. I can't. And then her friend says, that's easy, Helen. You just took an aspirin break. I just took an aspirin break. Bayer is the company, brings wonderful relief from the headachy feeling brought on by this hot, humid weather. Why don't you try it? So friend says, do like me. I take aspirin and I feel much better. I don't feel hot anymore. This is what people believed in the past. However, this is false. I mean, aspirin, of course, can treat a headache, can treat pain, can treat inflammation, but not hotness in the body. So if you feel hot, you should not take aspirin. These were very old advertisements, and usually chemical companies always want to say our drug is the best. It depends for what. Drugs can be good for one condition, but not so good for other conditions. Okay. So now an important point just to revise. Now, aspirin is sold in Japan also as bufferin. And Willow also produce similar drug, not aspirin, but makes salicin. So nowadays, why don't we boil the bark of willow? Why don't we prepare a potion when we have a headache? What do you think? Why don't we prepare a potion using willow bark like people used to do in ancient times? We have already said it actually. Why do we prefer aspirin to salicin? The answer is here. Go back to this slide. So in the past, people had this tea. We use this tea. Nowadays, we can still use this tea, but we also have aspirin. And we prefer aspirin to tea. Why? What do you think? Any idea? 京都はなんで薬を飲む?
Talk to each other. Let's
Yeah,
talk.
please.
And if you can, please tell us, share your ideas.
問題はない。
前に何をこちら作って、ゴールにこちら作るのが、何ですか、知らなくて、遊びに。Hey, nice to meet you again today. So, you too, right? なんでまず日本語でいいですか？どうぞ。 しょうもないなら日本語で話せで ID 入れてくれたら英語でまとめる。できるだけ英語で直接ついた方がいいけど、面白くないですか？自分で作ります。時間ですよね。そう、時間は大事です。他はありますか？そうですね。そうですよね。いろいろ入ってるからね。一種類じゃないから確かに。まだありますか？
Is easy to?
Easy to fix our diseases.
Yes. Yes. Salicin has some side effects. For example, it is irritating to stomach, whereas aspirin it is not. So that's one important reason. Aspirin has less side effects than salicin. And another reason, Okada-san just said, please if you want to. No?
Tea is not easy to take, drink, but aspirin is easy to take.
Yes. Tea is not easy to take because it is bitter. It is bitter, it's unpleasant. But aspirin is very easy to take because it's available in pills. You can drink it with water. So that's why also we want to use aspirin instead of salicin. And there's another, also one third reason, it's not here. There's one reason why we don't want to use salicin. And the reason is willow contains small amount of salicin, not so much. So if we want to extract salicin, we need a lot of trees. And there are not enough trees in the world to treat everybody. So we need help from chemistry. The nature can supply some drugs, but sometimes the amount is too small. We need to prepare those drugs ourselves. This is another reason, three reasons. So, how is it so far? 今までわかりますか? How many of you understand? Please raise hand.
大丈夫か？分かってない人大丈夫？
Okay. Thank you. So this is why we don't use it. And then we also have an exercise, but again, I'd rather skip because we have limited time. Okay. So later, maybe we should, but it's already time for a small break. So please have some rest.
JR の として、何時までに終わるって全部だから、3時まで終わるって分かるから。
Okay, shall we start again? We have seen one method to find new drugs. One method is extract some potion. Now we will see the second method to find new drugs, which is by chance. Sometimes, very, very rarely, sometimes we can discover a new drug by chance. For example, penicillin was discovered by chance. Penicillin is an antibiotic. Antibiotic is a drug that kills bacteria, or it stops bacteria from growing. Penicillin was discovered in around 1930 by Fleming, who was a British biologist. As a biologist, he was working with bacteria. It is possible to cultivate bacteria, to grow bacteria, using a special dish, circular dish called a Petri dish, and a gel. The gel contains some food for bacteria. Take a Petri dish, we add a gel. If we leave this dish in an oven or even at room temperature, after several days, bacteria grow. They are a little bit in the air, they stick to the dish, they eat the food in the gel, and they grow. One bacterium is very, very small, so we can't see. But many bacteria become visible. They gather, they form large groups called colonies. And when they form colonies, they become visible. Bacterial colonies, these spots. They contain many, many, many bacteria. So Fleming was cultivating bacteria on Petri dishes like this. And then something happened by chance. Another biologist was working in the same building on the top floor. He was also a biologist, but he was growing fungi, not bacteria. Fungi, in Japanese, kinoko. So kinoko are usually, the kinoko we eat are very big, but some kinoko, some fungi are very, very small. And they can also gather to form some colonies, some groups that look sometimes a little bit different. They have threads. And that doctor was cultivating fungi like this separately. And then some fungi flew in the air, escaped from the Petri dish and flew in the air. And they traveled one floor down until his lab. And by chance, some fungi stuck to the Petri dish with the bacteria. So that was by chance. And then something else happens. Fleming was a little bit a messy person. So he did not clean his bench very much. And one day he left a Petri dish with the fungi and the bacteria on his bench. And then he left. He left for a very long time, very long holidays. So during that time, the bacteria and the fungi had the time to grow. And when he came back, he found that there was an area, a circular area around this colony in which there were no bacteria, you see, just empty area. And he noticed that this was not bacterium. He noticed that this was a fungi. So he wondered, why is there such an area around the fungus? Why? And then he thought, maybe this fungus is making something, some substance, some chemical compound that kills bacteria around. So bacteria cannot grow very close to the fungus. Far they can grow, but very close no, because they will feel the substance and they will be killed. And then he decided to investigate. He repeated the experiment several times, and then he proposed, he said, maybe this fungus makes really some substance. And since this fungus is penicillium, he called the substance penicillin. This substance kills bacteria, so it is an antibiotic. This was the first antibiotic that people discovered many, many years ago. And penicillin was very, very important because it saved the life of millions of people during the Second World War. Now, usually, in a war, many people die. And there are two ways you can die when you fight a war. One is you are hit by a bullet and you die right away. You fall and you die. But there is another way that you can die. For example, a bullet, if a bullet comes to your heart, you die. But if a bullet, for example, hits here or the leg, you don't die. You just get wounded. And at the beginning you think, maybe it's okay, it's just a wound, I can get recovered. But after 2 or 3 weeks, happens, the bacteria actually that are in the air can enter the blood, and from the blood they go throughout the body. And then they infect all the body. And 2 or 3 weeks later, the soldier dies. This was very, very common, so many, many soldiers died because of this. And then penicillin was used as an antibiotic to treat bacterial infections in the body. Here we can see a soldier who belongs to the Red Cross, a special section, medical doctors, that injects penicillin into the body of a wounded soldier using a syringe. And so this was very important because penicillin was a kind of weapon, but a good weapon, a weapon against bacteria that saved lives of millions of people. So now we have seen fungi with penicillin, and here we see a syringe containing penicillin. But there is one question. So, the point is, Fleming discovered the penicillin, but he didn't know how to extract the penicillin from the fungi. So he wondered, I discovered penicillin, but I don't know how I can extract it from fungi. He didn't know because Fleming was a microbiologist. He was good at studying bacteria, but he didn't know how to extract drugs. So he asked for help to 2 other scientists, one biochemist and one pathologist. So he sent them the petri dishes containing the fungi and the bacteria, and he asked them, please help, can you extract penicillin? And then these two scientists were able to extract penicillin. How? How can we extract penicillin from the fungi? And the procedure is shown here. So instead of petri dish, we can use a simple test tube, glass tube. We can put fungi, water, nutrients, some sugar, and after several days, the fungi grow and produce penicillin. Then this mixture is filtered on paper, what happens is the fungi, which are here in red, remain on the paper filter. But the water containing penicillin goes through the filter. So we can separate the fungi from the penicillin by filtration. This procedure looks very easy. Filtration is easy to do nowadays, but in the past it was not. Penicillin is unstable in the air. So if you filter penicillin from the fungi, penicillin gets oxidized very quickly and it is decomposed. So you have to be very quick. And those two scientists did some sort of special filtration under vacuum using, they put this beaker, this one under vacuum. That way it was possible to avoid the contact of penicillin with air. And then the water is removed from the solution and penicillin remains as a powder. So it became possible to produce penicillin. But here the important point is the title, collaboration among scientists. So nowadays people think of penicillin and remember Alexander Fleming. Of course he was very important, but there were two more people who also allowed to isolate penicillin. And these three people worked together. If they didn't work together, today no penicillin would be available. So collaboration among scientists is very, very important. Each scientist is specialized in one different field, but if many scientists work together, they combine their strengths and then they can create something very nice. So very, very important if you decide to pursue your career in science, etc. It's very important you try to work together with other people. And then there was another problem. So fungi make penicillin, but they produce a very small amount. Only 0.04% of the mass of fungi contains penicillin. It's a very, very small amount. It means if you want to prepare a lot of penicillin, you need a very, very large amount of fungi, which is not possible. So how to do this? The government at that time of the United Kingdom and of the United States asked companies to prepare penicillin, but pharmaceutical companies were already very busy preparing other drugs, so they couldn't prepare penicillin. And then the government asked other companies, not pharmaceutical companies, but companies that prepared beverage-like fizzy drinks, for example, ginger ale or lemon soda, something like that. Those companies were using big tanks like this to prepare the beverage. And the government said, please stop preparing beverage and start preparing penicillin. So those companies changed job from beverage companies into pharmaceutical companies. And in this way, the tanks were filled with a lot of fungi and they were used to prepare a large amount of penicillin.
So at the time, the World War first, the time,
No,
era, the war time.
World War II, yes, II.
Oh, I see.
Yes. During the Second World War. Yeah.
Mm-hmm.
And unfortunately, so we also have to mention, unfortunately, that this is historical truth. At that time, penicillin was not available in Japan, unfortunately, because Japan and the United States were enemies at that time, and so it was forbidden for Japan to buy penicillin from the United States. After the Second World War, relationships improved, and then Japan was also able to make penicillin. But during the Second World War, penicillin was not available in Japan. In Japan, you could also only find another type of antibiotic, which was a little bit older, which was sulfamidic. The sulfamidics, but a little bit weaker. So during the production of penicillin, it was also important to build new buildings for the preparation of penicillin. And at that time, the companies who were building new buildings were trying to motivate the workers. And so they were showing posters like this to tell the workers, please work hard, please finish this building very quickly. The faster this building is completed, the quicker our wounded men get penicillin. Get this job, everything you've got means work as hard as possible. And eventually, when many companies started making penicillin, penicillin became wide available in the pharmacies, and so the pharmacies put a panel saying, now we have penicillin in stock, we can sell it if you need it. This is what a drugstore looked like in the Western countries at the time. You see, this is the window of the pharmacy, and these were all drugs. In Japan, drugstores look a bit different. You don't see the drugs from the window. To go inside, you have to ask the medical doctor, and then you get the box. But in Western countries, drugstore looks like any kind of shop, like shoe shop, a supermarket, and you can see the products from outside. Even nowadays, it's like this. So penicillin was very, very important. And why is penicillin so powerful? What does penicillin do to bacteria? You have seen penicillin. Please talk among yourself and give a reply in a couple of minutes.
So talk to each other. How much could you understand? ペニシリン最初はどういうふうに発見されたんですか？偶然だけど、ファンガイは真菌の意味です。キノコの真菌の種類で、ここではカビ菌を培養するこのプレートの上にカビちょっとだけ落ちてて、あの辺周りが菌が生えてこなくなっていたから殺菌法があったんじゃないかなと思って、でペニシリンが発明されたんですよね。で先ほどももともとジュース、ベラリーは犬のような意味ですよね。アメリカのジュースのこの会社が大きなタンクがあって、中にもともとジュースもいっぱいあって、そして戦争のためにもこのジュースの生産を停止して、でペニシリンを作るようにさせて、たくさんファンが中で増やして、でペニシリンを作りますよね。で大丈夫ですよね。で、so let's talk and try to think about the questions here.
analogy, comparison maybe. Let me take, let's say, this. Okay. This is a piece of paper, okay? What do you think? Can I break it or not? Is it possible? Yeah, it's, you know, if I hear it, it's broken. But can I break this piece of plastic? It's a bit hard. It's difficult to break it. Why? Why can I break this paper, but I can't break this? Why? Huh? Sorry? Paper is easy to break, but the plastic, not so much. Why? What's the difference between these two?
簡単っていうか皆さん結構言ってましたけど、もっと根本的なところ何が違うんですか？素材、
The material is different. Yes, the material. But a paper is very easy to break because as a material it's thin, but the plastic is another material. It's difficult to break. So the same thing happens with cell wall of bacteria, cell wall of our cells. The cell wall of bacteria is made of another material than our cells. So penicillin can cut, can break that cell wall, but can't break our cell walls. That's the reason.
Can you understand? ペニシリンは菌殺すだけど、私たちは飲んでも大丈夫です。もしすべての細胞をアタックしようとしたら、我々薬飲んでても我々は先に死んでしまうんですよね。で、じゃあなんで菌だけ殺して我々の体には大丈夫って言ったら、材料が違いますよね。菌の表面にはセルウォーがあります。我々の細胞の表面にはないから大丈夫です。
So this is why. And now there is another aspect. This is the structural penicillin, quite big molecule. And we can actually make penicillin at home because sometimes the mold that is in the air sticks to bread and uses bread as a food, so it grows on the bread and forms like a green, yellow layer and makes penicillin. So actually, if we take that mold and we rub against a wound, we can sort of treat ourselves. It's risky, we shouldn't do that because there are many types of mold on the bread. Some molds make penicillin, which is good for our health, but other molds make toxic substances. However, if one day, for example, we cannot find any drugstore open, example again in case of war, etc., we could use that as a last emergency source of penicillin. So, of course, this is a sort of joke, but it is true that there is some penicillin on the bread. So, next time you see something like that, of course it's disgusting to see, but it is also nice to think that there is some drug on that bread. And then, so this is the structure of penicillin. It's quite big, a little bit complicated, not so easy to prepare in the chemistry laboratory. But it is possible. We can make it. So, nowadays the fungi can be cultivated in large amounts using big tanks like this one. Very big. And inside the tank we can control temperature, we can control pressure, we can control the amount of food that the fungi have. So we are able to make penicillin in this way. But do you think this technique is still used to make penicillin? Is it still helpful? And why? This technique is possible. It exists. But do you think it is very common or not? Again, maybe 2-3 minutes or 5 minutes of discussion among you, and then we can reply. Okay?
Okay, you got a question and you have 2 minutes for that. Talk with your group members and think about it. Which one do you prefer? Which method do you prefer? PPT に聞こえたら済んだと思います。
They used to make nowadays. I think that
昨日も来てたの？はい。2日目なんだから少し積極的に発言しよう。
Now actually, pleasant part comes because we will play a game to understand this concept of drug development. And if we know the structure of the receptor, we can know which shape of drug we need. But sometimes we don't know the structure of this receptor. So we simply have to test as many compounds as possible, and we need to find which one fits into there. It's like when you have a door, but you cannot see the hole, you cannot see the lock, and you have many keys. And which key does fit into the hole? If you see the hole, then you can choose the correct key. But if you don't see the hole, like for example you are blind or you have a bandage in front of your eyes, then you don't know, you have to try many keys until you find the good one that opens the door. And this is what happens in drug discovery. We have to test many compounds. And this is what we will practice now. So, on your bench, each group has this material. Please check, please open the bag, the plastic bag that you have, and check that you have these pieces. 1 black, 3 blue, 3 red, 3 green, and 7 pieces of fake banknotes. Please check you have. And after that I will explain the rules of the game. Yes? Raise your hand. Everybody. Yeah, but just photo acceptance. Okay. It is used, but it is not so common. It is not so common. We can use it, of course, because we know that fungi produce penicillin, but we don't use it so much. Because we said fungi make very little penicillin. So to prepare large amounts of penicillin, we need very, very big tanks. And it's too much. We need too many tanks, and then the procedure is too complicated. Therefore, we prefer to prepare penicillin in a chemistry laboratory using chemical reactions. So nowadays, Fleming at that time took penicillin from the fungi, but nowadays we make penicillin in a chemistry lab without using fungi. Okay, so that's an important difference. Again, this is another example. We found something in the nature, in the fungi, and we prepared the same thing without using the nature. And also we should add, penicillin was one of the very first antibiotics. But after penicillin, many other antibiotics have been prepared by chemical synthesis. And some of them do not exist in nature. Only man has invented those. And so again, we can take inspiration from nature. Okay, so this is for the second part, and actually we were supposed to have another break now, but what do you want to do? Shall we continue? Do you want to take a break? Break?
ブレイク欲しい人手を挙げてください。
まあ、今から頑張って。
そう。これから続きたい。
トイレに
どれでも
したい人はあれだけど、いいわな。続きよう。いいかい ？Okay, go ahead.
Okay, thank you. So that was break time, but we have just a 2 seconds break time, and we go to the next section. So the third way of finding new drugs, by rational approach. So nowadays, we usually discover drugs by using our mind. We plan a new drug. But to understand rational approach, we first need to understand how drugs work. So what is the mechanism of action of drugs? Why are drugs active? Why can they treat our disease? Usually a drug works like a key. When the key enters a lock, it can open the door. And in the same way, a drug acts as a key. It binds to a receptor that is usually located on the cell membrane of our cells. And when the drug binds to the receptor, some reactions happen inside the cell that eventually have a beneficial effect for our body. This is why drugs are active. If drug binds to the receptor, is active. But if it doesn't bind, there's no activity. Okay? So drug is like a key, and receptor is like a lock, like a hole. And now we know that there are powerful drugs and weak drugs. Why? Some drugs powerful and some weak. So if the key enters the hole perfectly, if the match is perfect, then the key can open the lock very well. And then the drug is very powerful. But if the key does not enter the hole very well, it's a bit difficult to open the door. And that means the drug is not so powerful. Okay? Powerful drug means perfect match. Weak drug means unperfect, not perfect match between drug and receptor. This is a very important concept. So, if we want to discover a new drug, we need to know the structure of the lock. each lock has a different key. If we know the structure of the lock, we can plan rationally the structure of the key that is able to fit. This is another figure that shows the receptor on the cell membrane. The receptor is usually a protein, and the protein is very big, but this part is the site where the drug binds, so it's called binding site. Drug binds there. And sometimes we do not know what is the structure of this binding site. In this picture we can see it, but sometimes we don't know how it is made of. So we need to test many compounds. Sometimes we find that one compound binds to the receptor, but the fit is not perfect, and therefore the activity is weak. And then we need to change the structure of the drug so that it fits perfectly into the hole. In other words, we need to optimize. Optimize means we have to make it perfect. To change the structure from oval into rectangle into T-shape. And if the drug has a T-shape, it fits perfectly to the receptor, and then it is very active. What does that mean? Let's say, for example, this drug has this structure. It's a little bit like oval, so it doesn't bind very well. We need to add some sort of fragments into the positions 1, 2, 3, 4, for example. And the structure of the molecule changes, the molecule becomes bigger, and then it will fit into the hole. This is the optimization process. So, this is drug, that is weak drug. We add some pieces and we get powerful drug. So there are two steps. First, we have to find drug, and then we have to make powerful drug. Oh, sorry, my computer crashed now. So it will take me 2-3 minutes to restart it. Combination of fragments. Congratulations, this is the correct structure. Amoxicillin antibiotic. You compare the structure to that one to that of penicillin, you will see that amoxicillin is similar to penicillin, especially the black part. Black fragment is the same in both antibiotics. This amoxicillin is the modern version of penicillin. Penicillin, do you remember the poster with the soldier that injects penicillin? Penicillin can only be injected. It cannot be taken by mouth. Because if we take it by mouth, then the stomach will destroy it. But amoxicillin can be taken by mouth, so we can take it by pill. It's very convenient, like aspirin. So everybody can take it. It's very useful. So this is the second one. Then we will have one final game, last one, and then you will discuss all together. You will tell me which game was the most difficult, why was so difficult, and which challenges have you found in these 3 games. And then we will conclude the lecture. So, let's move to game number 3, which is this one. You see, you will get more complicated one. Again,
絶対にオレンジは
one.
オレンジは緑が1
Combination, right? All of you. So congratulations, well done. By using only a few backwards, you were able to find the correct structure, which is this one. 2 blue fragments, 2 benzene rings, and another red fragments at the end of the molecule. And the drug has 2 names actually. The name of the compound is fexofenadine. The brand name, the name that you find on the box is Allegra, and I was told that this is a very common drug in Japan. It's an antihistamine. Antihistamine means anti-allergic drug. So, well done. And now we will play another game, a little bit more difficult. Game number 2. For game number 2, you will get your money back. So you will start again from Nanaman N. Because otherwise it would be very, very complicated. And you will get new fragments. Please be careful not to mix the new fragments with the old ones. So please put back the old fragments into the bag. These are all the fragments you should have in the bag. Yes? Okay. So now the rules. So, we have 2 roles. You are the chemists and try to prepare new drug. And mentors and me are the biologists. We test your molecules and we tell you whether or not they are active. And then you and your group members belong to a pharmaceutical company that is trying to develop a new drug against allergy. Allergy is, for example, you take some food and you feel very itchy, you have allergy to that food, so you feel itchy. Then you need some sort of drug to treat that condition. And you have discovered that the black molecule, that black piece you have, shows some activity against allergy. However, it is not very powerful, so it's still not good as a drug. You want to change the structure of this molecule to make it more active. In order to do this, you can attach the color fragments to positions 1, 2, and 3. The color fragments will stick to the black scaffold by magic tape, creating a new molecule. So you can use these fragments. Now the goal of this game is to find the correct structure of the molecule. It's like a puzzle game. So you choose the color fragments and attach them to the black scaffold to prepare your molecule. you can use each piece more than once. For example, you can attach 3 blue, or 3 red, 3 green. Any combination is okay for all different colors. And any combination is okay. When you are ready, raise your hand. And a biologist will come to you and will tell whether the compound is active or not. But you have to pay 10,000 yen for that because biological assay is expensive. So the biologist comes, you give 10,000 yen, and the biologist tells you whether the compound is active. You will not be told which pieces are correct and which pieces are in the correct place. So you can say it's right, it's wrong, but we cannot tell you which ones are good, which ones are bad. You have to try many, many times for that. You can guess the correct structure as many times as you want, as long as you have money. If you run out of money, the game is over because your company gets bankrupt. So that's what happens sometimes. Companies spend a lot of money and they don't find any drugs. They get bankrupt. So it means you have 70,000 yen, nana money, and so you can have 7 trials, 7 guesses. Okay, so you start combining the pieces, and then when you are ready, please raise your hand and he will come to you. Okay? Did you understand the rules? Like this.
Shall we start?
Yes, please. Thank you so much. Good luck to all of you for your study. Good luck. And thank you for coming. Thank you. So now it's the moment of the truth. So I should know whether what you think. You see, this section is for speaker, and of course it's for me, but it's also you can also access. You go here, admin. If you click on admin, you will see a new page. It says administrator manage poll, and then you can enter the simple number 9001, and then you can click on open. And if you click on open, you will see this 81.3% thinks I was clear, 18.8 so-so. You have been kind, none of you said no, but you could have actually, and it's anonymous. So 81, about 80% yes, 20% so-so, which means 4 people, 4 to 1. Now there's 16 people, so probably 2 people said so-so, so thank you. Then I click back, enter poll number 9002. And 9002. And you can also check, you can do the same, open. 78.6% says it was useful. 7.1% it was no, not useful. I'm sorry, it's so maybe next time, you don't have to attend a lecture in the same topic, because it doesn't have to be useful for everybody. It may be helpful, so not so helpful for your studies. It might be useful for your culture, maybe. And 14.3% so-so. So thank you. And now let's check the ball number 3. Did you enjoy? Almost the same as usefulness. So 81% said yes. 6.3% did not enjoy. So boring. So sorry. 12.5% so-so. I'm sorry to those of you who didn't enjoy. Actually, but that 6% of you actually did not enjoy, doesn't think it was useful, but at least understood, because answer number 1 had no 0% of number 2. So it's okay if at least you understood some English. That was good practice for listening, maybe. So yeah. Thanks anyway. It took a while. So now there are 5 minutes to 4. Maybe. So let's say we should finish by 4. Please, yes. Only fill out the OPP sheet.
And also, can I correct the note first? Then you
Okay. They need to collect the things they wrote in the class first, and at the same time, students will be doing this for.
多分これ
使わなかったことは回収しようか。それ使ってないかな。
I think there are too many pieces to set molecular.
Too many places.
So
Pieces. You mean the colored pieces?
yes.
Yes. In the game number 2 and number 3, there were a lot of colors, a lot of fragments. that we could choose, and then we didn't know which one was correct. The higher the number of fragments, the more difficult the game. It's very tense. Yes, that's correct. And also, what about the central part of the molecule? If you check the first game, how many empty positions did you have? 3. In the first game, there were 3 empty slots. And in the second game, also 3, but more fragments. In this case, how many empty slots? 4. 1, 2, 3, 4. In this case, a lot of empty slots and a lot of fragments. So that makes the game very, very complicated. And actually, so the number of combinations is equal to the number of fragments. Fragments means the colored pieces, to the power of the number of empty slots. E.S. E.S means empty slots. This is actually a formula that we can use to calculate how many possibilities we have, how many possible combinations. If we apply this formula to, for example, the second game, the second game was this one. How many fragments, how many colors did we have here?
How many
How many colors? How many
coins?
possible fragments?
6. Yeah.
Yes. So the total number is very high. It's 3, 6, 9, 12, 15, 18. But the number of the colors is 1, 2, 3, 4, 5, 6. Only 6 colors. So in that case, the number of combinations is 6 to the power of the number of empty slots. 1, 2, 3. 6 to the power of 3. 6 times 6 is 36. Times 6. You are faster than me at calculating that.
216, 216.
216. So there were 216 possible combinations to find the correct structure. Most of you actually found it very quickly, so you were very good actually at finding the structure. But the larger the number of empty slots, the larger the number of fragments, the most difficult the game becomes. And
皆さん、コンビネーション、ずっとコンビネーションのことを言ってますけれども、そのコンビネーションの意味、英語の意味を分かっている人、どういう意味ですか？ Okay, did I? What's the meaning? では、せーの。Yes, okay, so この6種類のこのfunctional groups ですよね。3箇所、それでこういう計算し方分かっている人、せーの。Okay, good. Okay, go ahead.
So this was one challenge of the game. And what was the other challenge? Why were you? Sometimes you were very worried. You didn't know whether you wanted to try the combination or not. Why were you worried? What was the other problem? So sometimes you thought for a long time before calling us to tell you the answer. Why was it that?
You should ask the team 1.
Pick up one.
So you were hesitating a lot of you were hesitating. Why was it so?
自分たちが一番遅かったの。君たちが答える義務がある。
You were worried because what did you have to do? When you call us, what do you have to do to get a reply from us? So you called us, and then what did you do?
We have to pay money.
Money, yes. And did you have a lot of money? No. Only none of money, which means you only had a maximum of 7 trials. So that's another challenge. Drug companies also test chemical compounds to find a new drug, but every time they make a test, they have to pay money. And sometimes they try many times, but the compound is never active. And then they spend all the money and they get bankrupt. This is just a game. So even if you spend none of money, it doesn't matter. It's a game. But in reality, chemical companies are very worried because if they run out of money, they are out of job. This is another challenge. So the first challenge is the number of combinations. 216, and actually, in reality, you know how many chemical compounds we can make? How many chemical compounds in theory we can prepare? In this case, only 216. But in reality, how many possible chemical compounds are there? How many? Many, a huge number. It has been estimated because it's a very big number. 10 to the power of 60. It means 1 with 60 zeros. Billions of billions of billions of billions of billions of billions of billions. Huge number. It's impossible to make all of these compounds, of course. So we can only prepare a few. But if we prepare only few, sometimes none of them is active. So first challenge is many compounds are possible. Second challenge is money. Third challenge is, so maybe sometimes you got some help, little help from us. Sometimes we also gave you too much information, sometimes, so that was okay. It was a game. And in reality, we never know. We only know yes or no. Compound is active or not. The biologists themselves do not know which fragments are correct, which fragments are not. And also, I noticed some of you have found the correct combination, and then after you found the correct combination, you covered the structure because you didn't want other people maybe to copy it. Or you suggested solutions. And that is also okay. But in reality, there are many chemical companies, and they never speak to each other because they are in competition. When one company finds the good drug, that company sells the drug and makes all the money, and the other companies are out of game. In this case, you noticed we waited until all of you found the correct structure because it's a game. But in reality, there is only one winner. Only one company, usually. Yes, unless in very rare cases, 2 companies decide to work together. Usually they don't. So that's a challenge. There's a lot of competition, and there's a sort of secrecy when a company finds a new drug or is about to find a new drug. They never say, oh, we have almost found a new drug. Never say, because otherwise other people will copy. So this is another challenge. in drug discovery. And then, these are the main ones. There are more reasons, but I would like to finish by 4. And you also have a questionnaire that might take you 10 or 15 minutes, plus maybe another 5 minutes for the OPP sheet. So it means now it's 3:35. I have 5 more minutes before finishing up. Anyway, you will get the printouts of this presentation, so you can read everything at home. Okay. So these are the other challenges, but we don't have time actually to discuss this. Anyway, it's very risky. Finding the proper key into the lock is only the first step. Let's say you have all found the correct active drug. But that means that that drug binds to the target, which is the lock. After that, there are other steps that have to be clear. We have to make sure that the drug is also active in the cell. Sometimes the drug is active against the target, but is not active in the cell. After it is active in the cell, we need to make sure that it also works in animals, like mice. If the drug works in the mice, then we try it on men. Sometimes the drug works on men, but it has side effects. It's also very toxic. So in that case, the drug cannot be put into the market. Starting from 10,000 compounds, eventually only one becomes a real drug and enters the market. This means that the pharmaceutical companies have to spend a lot of money, and, but they're not sure whether they can get the drug. When eventually the drug is approved by the authorities and is sold, sometimes it's very expensive. And one reason why drug is expensive is that the company had to spend a lot of money at the beginning, so they need to take the money back from sales, one reason. Okay, so there are several steps that have to be cleared. And then another very important concept eventually. We have spoken about drugs. What is the opposite of drug? A drug is very good for us. And what is the opposite of drug?
The opposite of the drug is bad.
薬の反対はどうですか？何ですか？
Poison.
Yes, poison. Poison is the opposite. It's very toxic. So, and we think drugs and poison are very different. For example, here we have aspirin and we have arsenic. This bottle we find also a sign, a symbol. So which one is the drug and which one is the poison? Is aspirin a drug or a poison?
Drug.
Drug. We have seen earlier it's a drug. What about arsenic? Is it a drug or a poison? Poison. It's actually, in most cases, it's a poison. However, the difference is not so clear because arsenic actually can be used as a drug, but it has to be used in very, 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 very small amounts. You see, trisonox is arsenic trioxide, means arsenic that binds oxygen. And it is used at a very low concentration, 10 milligrams per 10 milliliters. So it's a very diluted solution. It's very small amount. And if we take a small amount of arsenic, then it becomes a drug and can be used to treat leukemia. Leukemia is a type of blood cancer. In the blood we have several types of cells, one of them are white cells. And sometimes the white cells multiply too much. And then they eat the other red cells and the other cells in the blood. And then our blood cannot work properly. And that becomes a cancer. This drug can treat leukemia. So, actually, arsenic can become a drug. Also, aspirin. There are 20 tablets in the box. How much aspirin we can take every day? If you have a headache, how much aspirin do you take? Usually. How many pills? Maybe 1, 2? Probably 2, maximum 2. Yes. Actually, aspirin is a very safe drug, so we can take up to about 4 grams per day. But if we take, what happens if we take 1 full box of aspirin altogether? 20 pills altogether. 20 pills, each pill is 500 milligrams. So we take 20 pills, means 5,000, 10,000 milligrams, 10 grams of aspirin. The aspirin becomes a poison, and we can die because of that. So, what does it mean? It means that the difference between drug and poison is not neat. Whether it's a drug or a poison depends on the dose. The dose makes the drug or the poison. It was 500 years ago, there was a medical doctor in Switzerland, Paracelsus, who found this concept. It says the dose makes the poison. If you take a small amount, the compound can have some good effect, but if it's too much, it becomes toxic.
ドーズの意味大丈夫ですよね。脱水脱比のダーズだけどここではドーズで言います。名詞です。意味はわかりますか？薬の効用量どれくらい投与しますか？
理由僕教えてあげる。いやいや大きな声でみんな、いやどうする？
ドーズの意味はここでは名詞として発音はドーズで言います。意味は薬とかケミカルとか薬ですよね。薬のメインですけど投与量書きましょうか。
そうだね。
ここで書きますね。ここで書きますね。これです。
それで理解したね。
発音はダーズではなくて、ドーズです。はい。So, am I clear? Do you understand me? 今大丈夫ですよね。Okay.
Very last slide before we do that. So why is it that? Let's take another example, which is very common. In Japan, usually people take tea. Tea wakes up us because it contains caffeine. In other countries, people take coffee, which also contains caffeine. So caffeine can increase our level of attention. If we take caffeine in a low dose, let's say 1 cup of coffee, 2 cups of coffee, then caffeine is a drug because it can bind to some targets in our brain and it has a therapeutic effect. It increases our attention. But if we take, let's say, 10 cups of coffee, 20 cups of coffee, just one after the other, what happens? Caffeine in high dose. Of course, yes, the caffeine will act on the same target in the brain, so we will feel very attentive. But at that dose, the caffeine also binds to another target, that is the heart. And it will increase the heart rate. It means the heart will start beating more quickly. And then the blood pressure will increase. And if the blood pressure is too high, it's dangerous because some blood vessels can explode. So caffeine is toxic. 1 cup of coffee is beneficial. But if we take more than 36 cups of coffee a day, we can potentially die. So again, the dose makes the poison. You see, so this is just one key, but if the dose becomes too high, the drug becomes like a double key that can bind multiple targets. Okay, so this was the last slide. Then one way to discover drugs is to mix substances together. You want to find something new, but this is very dangerous. You should never do that in a chemistry lab. And now I would like to ask you feedback. So previously I asked you, do you have all mobile phone with internet access? You all have. If some of you don't, please use a mobile phone from some of you. If possible, please scan this QR code and you will access this website. On this website you can vote. Please enter this poll number here. And this number corresponds to this question. Was lesson clear? Then you click vote. And when you click vote, you will see a new screen. And you can choose answer 1, 2, or 3. Yes, no, so. Okay? And please make your answer. It's anonymous, so nobody will see. You can really tell what you think. If you think the lesson was not clear, you can reply no. And nobody will know. In the end, I will only see how many people think yes, how many people think no, how many people think so. But I will not know who you is. So it's a very good system for you. This is like voting. When we go to elections, we vote for our political representatives. The vote is secret. Nobody knows for which people we vote. It's the same system. And it's very important for me. It doesn't matter to know which ones of you think the lesson is good. It's very important to know how many think it's good or not. Okay, so please either scan this code or please go on that website that is indicated and enter first this number and reply. Then again, go back, enter this number, reply, enter this number and reply, okay? Please.
So, I'm sorry, you want them to do it now?
Yes, now, yeah.
So take out your smartphone and you may scan the barcode
持って
here.
ない人いるんだっけ？
持ってない、これぐらい何持ってない人。持ってない人だったら、このウェブサイト、この HTTPS、それ、オンラインクリッカーですよね。これ書いて、これです、こっちで。家に帰った後に、そう、パソコンでアクセスしてくださいね。This is the online questionnaire。オンラインのアンケートです。トップ名で皆さん自由に考えたことを関心したことを答えてくださいね。Yes か No がまたはそうか。Just feel free to come here. Just come here.
いやいや、持ってないって言って、今持ってなければ。
今じゃない。
いやいや、分かる持ってないです。パソコンからやれるんで、もちろん。大丈夫です。
And then they will print it out and students. It's a very good system.
事でいっぱい投資できるわけやな。そういうのですか。ちょっと思いついてしまった。
これのボットなんだ。
If you finished, please put your smartphone back into your bags to show us that you finished. 終わったら携帯戻してくださいね。終わったっていうことを戻してくださいね。
質問が3つありますね。
Okay.
So, after replying to the first one, please go back and reply second and third. Enter different numbers.
So make sure that you answer all the 3 questions here. Okay? You go this one, you come back, and answer next, and come back again. So,
スキャン違うこういうことか。もう遠慮なく使う。多分1枚には出てる。1枚
つながないといけないから。そういうことあるために。
いいやつ。
これもわかる。飲みに行かない。そうか。いくらですか。
So we have finished. We have all found the correct combination. Congratulations again. And this was the correct structure of the drug. The chemical name is atorvastatin, and the brand name is Lipitor. And this is the mechanism of action. It's the drug inhibits, means it blocks an enzyme that has a very long name. And when this enzyme is blocked, our body stops making fat. Sometimes we can get fat because we eat a lot of oil, oil or meat, chicken, etc. Or sometimes our body makes fat itself. And if we take this drug will stop the production of fat in our body. Fat has chemical names called cholesterol. Cholesterol is the correct name. So lowers cholesterol in the blood. Now, to be fat is actually it's not so bad. Of course, we look a little bit big, but that's actually not such a problem. Problem is that the fat in our body can actually gather on the blood vessels, and in the blood vessels it gathers, and the blood vessel becomes very thick. You know that sometimes the blood vessels need to dilate, sometimes they need to contract. If we run, for example, a lot, then our muscles need a lot of oxygen, and in that case the blood has to go to the muscles to bring oxygen. So the blood vessels have to dilate to carry blood. But if there is a lot of fat in the blood, the fat forms a layer inside the blood vessels, and then the vessel cannot dilate. So the blood cannot flow very well, and this is bad. And sometimes if the blood vessels in our brain become very, very thin, then the oxygen sometimes does not arrive to the brain, and some parts of our brain die. And then we can have very serious problems. So it's very important to lower cholesterol. And one way is to take this drug. Another way is, of course, to eat very healthy food. Japanese diet is very, very healthy. It's not so fat. So this is very convenient. In other countries, United States, United Kingdom, Europe, they have very fatty diet. So people can get fat very, very easily. And this drug helps a lot in that case. All right? So this was for the third drug. And now, please tell me, how was the game? Did you enjoy it? Was it nice? I think most of you enjoyed it. And was it difficult or not? Some of you actually found the correct structure very quickly. Others maybe after a while. What was the main problem? Which game was the most difficult one? The number 1, number 2, number 3? Huh? Number 2 or 3? 3. Number 2? Any? How many of you believe number 1 was the most difficult? Huh?
No one.
No one. How many of you believe number 2 was most difficult?
Number 2. Yeah. Okay.
And how many of you believe number 3?
Okay, number 3.
Okay, 3. Actually, yes, the number 1 was the easiest. Number 2 was so-so. And number 3 was the most difficult one. Why do you believe that number 2 and number 3 were very difficult?